you. Next speaker is Pierre Peterlongo.
Hi everyone.
kmtricks, efficient construction of Bloom filters for large sequencing data collections. So yes, we can see your screen.
Great.
So I think we are ready. Yes, everything is fine. Please go ahead.
Okay, thank you. Hi everyone. So I'm indeed Pierre Peterlongo, and I'm going to present this work that was done in collaboration with those three great guys, Theo, Paul, and Rayan. And Theo is the one that coded and made available the tool. So this is mainly his work. So I'm going to talk about kmtricks. It's a tool for constructing Bloom filters for a large sequencing data collection. And I'm happy to present now because we saw just two talks about using of counted k-mers, or tools that arrive after the step of counting the k-mers. So we need very efficient tool for doing this task and creating Bloom filters, and this is exactly what we want to do now. My main motivation, I think we all know this, so there are more and more sequences. They are doubling currently almost every 2 years, and so we need tools to scale up to these datasets. And in particular, if you're interested by a sequence, whatever it is, a gene, something, there is no way to query all those treasure of available data today. And it's really a shame because, as I said, it's a treasure. We put a lot of money, a lot of energy to sequence those data, but we are not able to use them in our daily life as a researcher because they, as indicated here, they sleep in rarely open drawers. So mainly when you obtain sequencing data, what you do is to analyzing them after assembly and mapping, for instance, and then you put them somewhere and you forget them for all the rest of your life because we are not able to query them. So this is what we would like to propose. And for doing this, we all know that we use a lot the notion of k-mers, so these words of length k, and the idea is to be able to propose an index for a huge input set of samples. Propose an index here represented by this black box, and this index is able to tell you for each create k-mer in which sample this k-mer occurs or does not occur. And this talk is not going to propose a new index, it's going to talk about this green arrow, and we're going to propose a small part of this green arrow, but this is a kind of important part, I think. We're going to talk about Bloom filters. To store the k-mers, so you know that we can store the k-mers in different way, but one of them is to use Bloom filters. If you look to most recent methods for indexing k-mers, many of them, the blue ones here, use the notion of Bloom filters, and this is why we are especially interested for proposing this kind of representation. So Bloom filters, I'm not going to remind you what they are. What I would like to say with this slide is that usually when you want to deal with k-mers, you first have to count the k-mers in order to have their count, and also to remove low abundant k-mers that you may consider as false positive, as Yoshihiro said. And so these two steps are, take a lot of time and can be improved following two directions. So we can make them more efficient, in particular when we have many datasets and when we are just interested by Bloom filters. And also, importantly, we could consider low abundant k-mers as erroneous, but also as informative. For instance, when you're dealing with metagenomics data or transcriptomic data where abundance is uneven, and you can have very low abundant k-mers. So this is what we want to do with kmtricks. So what we propose is a way to count directly hash values instead of counting k-mers and then later transform them into hash values. And we propose another way to rescue low abundant k-mers that could be erroneous, but that may be non-erroneous k-mers. I'm going to explain to you all this stuff. Just to have an overview of the input-output of kmtricks, what it is. So kmtricks inputs are a set of resets. So we represented 2 here, but we can have thousands of datasets. And mainly you can ask for 2 distinct representation of the k-mers, or either as k-mers, so it can be counted k-mers. For each k-mer you have is number of occurrence in each dataset, or only presence-absence matrix. So same thing, but you just know if the k-mer occurs or not. And the main novelty is to directly compute the same thing, but not with k-mer representation, but with hash values that tells you for each hash value its presence or not in each dataset. This vertical representation of the hash value gives you what may be called or had been called the color aggregative representation, and we also represent it in a horizontal fashion. So this is this vector, but here it's horizontal, and here this is what is called k-mer aggregative. So for each dataset, you know the k-mers that occur inside, or the hash values in this representation. Right, I hope this is clear. And I'm going to dig a bit into not the algorithmic details, but the overview of the pipeline. So the beginning of the pipeline is classical. We use minimizer, partitioning, and super k-mer, as this is usually done, for instance, in KMC. So the first step is to compute a set of minimizers that will spread the k-mers into different partitions. So the goal here is to find an balanced way of spreading the k-mers into the different partitions. But this is classical. Then we put every k-mer in its own partition, and doing this we also compute the super k-mers in order to save time. And then arrives the classical, again, step of counting. So once we have all the k-mers stored and sorted in their partition of their dataset, we just have to read them to count them. So this is what is done usually. What we propose, what is specific here to kmtricks, is to directly count the hashes, not the k-mers, but the hashes of the k-mers. And this is what is represented here. So for the first partition of the first dataset, we know that the hash value 2 occurs 3 times, and the hash value 3 occurs 8 times, and so on. One important point to notice here is that the addresses, the set of addresses of each partition are consecutive. So for instance, here in the first partition you have addresses from 0 to 3, and in the second one you have addresses from 4 to 7, and so on. And this is going to be useful later. And so we can propose these counted hashes, and we can also, of course, propose directly the Bloom filters. And then, once again, we go a bit deeper in what is specific to kmtricks. This is this notion of merging and of aggregating partitions in order to save rare shared k-mers, as we are going to see. So the idea here is to merge all all identical partitions. So for instance here, for partition P1, we are going to merge all the data from dataset 1 and dataset 2, and this is what we can see here. So this is, we just walk the files together, and we just write down all the k-mers, all the encountered k-mers with their respective abundances in their dataset. Depending on the user choice, we can do this either for k-mers or for hash values. And for hash values, the small subtlety is that we fill the hash values as if it were directly a Bloom filter. So this means that, for instance, the hash value number 1 was never seen before here. So we are going to put some empty lines of 0 corresponding to those hash values. Of course, the hash values here are written in this slide for the example, but we do not write them. We just the hash values correspond to the line IDs. All right. I hope it's all right. And here come the kmer or the hashes rescue. The idea is quite simple, actually. The idea is if a kmer has a very low abundance, so very low is below a threshold, user-defined, possibly per read set, but anyway, it's low abundant kmer. Maybe this kmer, as in this example here, so this is, well, it's not a kmer, it's a hash value, but for us this is the same thing. Let's say this kmer has a very low abundance in the first dataset, so it would have been removed by classical solutions, but this kmer has bigger, or at least it can be said solid in some other datasets. So maybe, of course, maybe, this is a kmer that is not due to a sequencing error, but this is a kmer that came from a low abundant species or a low abundant expressed gene in the dataset 0. So in this case, if it's low abundant but with a high abundance in one or several other datasets, so this depends on the parameters you will choose, you can rescue this kmer. So this is what we call rescue, and this kmer has been rescued here. This is not the case, for instance, for this kmer because it's low abundant everywhere. So we are not going to rescue it. And for doing this, we need, of course, the holistic view of the occurrences number of the kmer in all the datasets. And this is what is permitted by this merging step. Okay, we are almost done now. Just what remains to be done is to transpose those matrices, well, let's say here, those matrices into a horizontal view in order to finally output the Bloom filters if they are required by the user. So we have an arrow here, but also one here in case you are not interested by the rescue process. And I'm done now with this pipeline. I hope it was clear. And I would like just to give you a bit of results. So as we saw before I described the pipeline, we have several possible outputs depending on your interest, and many parameters that are described on the GitHub, but you can choose how to rescue kmers and how to represent the output and so on. So you can ask for a kmer matrix construction with or without the abundance, the Bloom filter construction, you can ask for the rescue or not, and so on. So you have a lot of possibilities. And what we choose to show to you in this talk is the result we obtained by combining kmtricks that computed some Bloom filters for some input dataset with our DSBT. So our DSBT was presented in DSB 2 years ago, if I remember correctly, by Paul. And this is also, this talk from Paul was also one of the motivation for this work. So once again, DSB is a great workshop. Sorry, what I was saying. Yeah. Just a small technical point here. We propose a modified version of AOD because we have a modified way of computing the hash addresses of a create kmer. So we need our own way to query the Bloom filter. So this is why we propose on the kmtricks GitHub a compatible AOD SBT version. And so we made some experiments and we show you some results on Sara Ocean data. So for those that do not know Tara Ocean, this is this great boat that went all over the world, and it's still is somewhere here now, I think. But this is this boat that samples seawater metagenomes, and we choose to focus on all bacterial metagenomics data from sampled by this expedition. This represents more than 6 terabytes of compressed FASTQ files, and we obtained the following result. We compared our results, so kmtricks, with what could have been done by using a kmer counter tool such as Jellyfish or KMC, in combination with the make-bf module from our DSBT. So this is a module that takes counted kmers and creates Bloom filters from those counted kmers. First, the time. So kmtricks went faster than other tools because it's dedicated directly to construct those Bloom filters. So hopefully this is what we were looking for. So we are between 3 and 4 times faster than Jellyfish and KMC plus make-bf. In terms of RAM memory, well, we are also the tool that uses the less memory, but as you can see, this is not really an issue. However, as we use a lot the disk for temporary computations. We use a large amount of disk, almost equivalent to the input size of the dataset. However, here this disk usage is quite high because we asked for the rescue step, so we had to go to the merging process. We had to write all partitions and all datasets on disks, and we also conserved all kmers here, including those occurring once, in order to be able to rescue them in the second step. And this explains why we use so much disk. If we used kmtricks in the same way that what we did here, so without rescue and removing all kmers in once, we would have achieved something similar. Not, we haven't done this. This is an estimation, but we have to verify it, to verify this. But we should have the same kind of disk in this situation. And this is a bit out of the scope of the presentation, but we still constructed the final index on this dataset. So we used, as I said, our DSBT. So on top of the constructed Bloom filters, it took almost 40 hours to construct the final index, which final size is 600 gigabytes. And you can query this index with some sequences, and it takes, for what we did, 19 minutes. Whatever if you query one sequence or 1,000 sequences. So it seems that the time for loading the index in RAM takes a lot of time. We still have to investigate this, but this is what we are thinking. And of course, now I have to show you how the rescue process work. Does it work or not? So you know that usually, as we saw also, you have this kmer spectrum, and you can decide where to cut to remove what you consider as erroneous kmers. But for instance, here it's a Tara Ocean sample. You cannot see this, so you cannot decide how to remove that. And removing low abundant kmers is not always a good solution. And so what I would like to show to you is what here we can see what would have been done without the rescue process we propose. And what we show is the ratio between the number of kmers that are removed if you remove simply kmer occurring once, divided by the expected number of erroneous kmers. Because I'm not going to explain this, but we were able to compute the expected number of erroneous kmers. And what we see on this plot is that this ratio that would be equal to 1 in an ideal case is bigger than 1. So it means that we remove way too much kmers. Now, if you look to the result we obtain with the kmtricks process, and if you plot all the kmers that were removed after the rescue process, so the unrescued cameras, sorry. And if we plot the same ratio, you can see that we are much closer to 1. So we are pretty confident in the fact that we removed the good cameras, but this still has to be proved. Okay, and I will finish with this conclusion slide. So maybe the main take-home message is the first line here. So we improved BF construction time by a factor of 3, and it's good, but it's still very far away from being sufficient to hope to scale up to the whole databases we want to index. So there is still a lot of energy and a lot of work to put in this research. I'm very excited by these ideas. So we built the index for Tara Ocean. We show that this low abandoned camera rescue provides statistically relevant results, but we still have to analyze precisely from biological point of view what are the cameras that we kept and we removed to validate this. And finally, for the future work also, we would like to take advantage of this partitioning of the Bloom filters we proposed before the merging for improving the construction time of indexes, for instance with Audi, and also to improve the query time by taking into account these 3 possible partitions. The GitHub is available here, and once again, I would like to emphasize the fact that there was a lot of work made by Theo, and this tool should be end-user ready. And something important to say also is that it contains a lot of modules, a library that you can use independently. So please use it, and we are happy to have your feedbacks and your questions now. Thank you.
Thank you very much.